Hello, everyone. So we're going to give everybody a minute or two to join. But thank you for being here with us tonight. I recognize some of the names, but some are definitely new to me, so welcome. And I apologize in advance from any noise of small children out in the hallway in case they get really close to the door.
A friend of mine, this is jokingly, a friend of mine used to say, babies are like New Year's resolutions. They should be carried out. So welcome people. I know we'll wait a few more minutes or
Yep.
Another minute for people to join us, but and Mirka will introduce me in a moment.
Okay, so and there was a question already in the chat. How do we see if our sound or video is on? So everyone has been admitted to this automatically muted and with your video off. So I, for example, can see that you're in the room, but I also can see that you're muted. And so the way that we do this, for those of you who haven't been to a Superstellar Friday virtually with us before, Dave is going to be talking and I will be monitoring the chat and I'll be monitoring the Q&A box as well. So you've got ways to ask questions, but you can also raise your hand. And if I see that your hand is raised, like someone just did a moment ago, what I will do is I can unmute you and then you'll have a chance to ask your question verbally. But otherwise, you're at the moment, you are specifically muted and your video is shut off so that way we're not getting, unfortunately, you probably are getting some of the noise that's happening in my hallway right now because someone's refusing to wash his hands after dinner. But that way we don't get any background noise and hopefully there's not too much talking over each other. So I see that someone named, the name looks like Kaladin or Kaladin has raised their hand. So what I'm going to do right now is I'm going to press a button. That means that now they've been allowed to talk. If they have a question, they need to unmute themselves and then they can say something. So that's how this works.
Awesome.
Now, just to let everyone know about the general schedule, I think we're getting close to having everyone here. So Dave will be talking. He'll be stopping to ask questions of you because this is supposed to be about having fun with math and that kind of thing. You'll have a chance to ask questions periodically throughout the presentation and then also at the end. So there'll be a couple of different ways that you can interact. And for those of you who are unfamiliar with the Q&A option, so you can use the chat. And you'll see that that's an option down across the bottom of your screen. Typically, you'll see you can get to the chat. There's also Q&A. If you put a question in there, other people can see the questions and can like them or vote for them so that way they rise to the top of the list to get answered earlier. But you're welcome to use either of these, or you can also simply raise your hand and then I'll unmute you and you can ask a question as well. So I think we're good. If anyone else arrives, we'll try to catch them up. But thank you very much for joining us for another iteration of our virtual Superstellar Fridays. We definitely miss seeing everyone in person. It's a different medium, but it does mean that we get to do a variety of things in terms of how we interact and the topics that we can hit and where we can be while we're doing this, which is pretty cool. And so tonight we are getting back to math again, which is fantastic because sometimes we kind of don't always include it in the stuff that we're doing here. So our own Dave McDonald, who is an educator both for us and also at Belmont High School. He is very knowledgeable about astronomy. He is very knowledgeable about mathematics. So he is here to show us how we can have fun with math, some things that we can do with it. And I'm going to mute myself in a moment, and then I'll just be monitoring the chat and the Q&A and just kind of facilitating any discussion. So Dave, thank you so much for being here.
Well, Mirka, thank you for the introduction. And it's a Pleasure to be here as always, and I welcome everybody who's joined us, and there may be, a few people who trickle in along the way. And I'm delighted to be here, and we're going to talk about fun with math. And at the end of the presentation, I'm going to show you how you can win, or at least improve your odds of winning the car, because you don't want to get stuck with the goat. I'm going to tell you how to improve your odds when you play the game. Let's make a deal with Monty Hall, but it'll be let's make a deal with Dave McDonald. Well, we're going to get started. And as Mirka said, make a note, raise your hand, make a note in the chat, and I'll try to address those along the way as appropriate. So I'm going to just start by my presentation, and I will have various introductory remarks along the way, and introductory remarks for each of the slides. So I got kind of a broad range of things that hopefully would be of some interest to elementary, middle school, high school, college, adults, and people who know a little about math, and maybe people who don't know much or remember much, because I'm sure we all learned it at one time. So let me share my screen with you, and let's see. We're gonna go to that, see how that works. Okay. It looks like we're on the air, and I have a couple of lights, so I may be moving my head around to see what I need to see, because there's some lights blaring in my eyes. So math is fun, and what I thought we would start with is the idea of some patterns. So here's an example. 1 times 1 is 1. 1, which is 11, times 11 is 121. 111 times 111 is 12321. And you can see the pattern. I'm not going to read them all, but as you go down the list, I'll stop here in the middle. 111, 111 times 111, 111 is 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. Like if you were to do the math on your calculator, that's what you would get. Kind of interesting. You don't need to have a calculator for this program. You're welcome to if you want. A little later, having at least a scrap paper and a pen or pencil will be helpful. There's one place where I'm going to ask you to do something at home on, and it's simple math. You don't need a calculator for it, but if you have one, that's fine. But now let's look at the bottom. We've got this number here, which is 1,111,111,111, right? 111111111 times the same thing. And notice the result, if you were to do this on your calculator, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2, 1. Just cool, right? So some of these things, as we look at them, like I'll bring up the next one that I have for you. You may ask, well, gee, what makes it work that way? And we could get into that, but just like art, think about art. I taught an art appreciation course for high school one time, and I brought my students to the Boston Museum of Fine Arts. So I've got 20 or so high school students, and we go in, and it's a big place. If you haven't been there, it's a big place, all kinds of art everywhere. Go look at the art, enjoy the art. Well, a half an hour later, they're all done. It's like, what? Because they don't know what they're looking for. For the artists, the brush strokes, what's the medium they use? They use a thin brush or a fine brush. How do they mix their colors? How do the strokes go? We know Van Gogh likes to use a lot of circular motion in his strokes. And so, but you can enjoy it. You can look at the art and say, wow, that's really interesting. The Mona Lisa. Is it a reflection, or is Rembrandt actually kind of hiding under her face? Is it a self-portrait of some sort? Well, people who know a lot about art can study it, but anybody can just look at it and say, wow, that's pretty neat. So that's kind of the avenue here, because we have a limited amount of time. So just look at this and just kind of say, oh, wow, that's pretty neat, without me taking 10 minutes to kind of explain why it works this way. Just appreciate, look at this. You see what's happening. I have my little pointer here. 1 times 8 plus 1 is 9. And you'll notice we're going to multiply everything by 8. And then to the 1, I'm going to put a 2 on it. So 1, 2 times 8. And then I'm adding the number that I put after the previous number, and I get 98. Then I put a 3 after the 2. So I get 1, 2, 3 times 8. And then I add the 3 that I put behind the 1, 2. And I get 987. And so you see the pattern follows 1, 2, 3, 1, 2, 3, 4, down here 1, 2, 3, 4, 5, 6, 7 times 8 plus the 7, which is what I added behind all the previous digits. And that's 9, 8, 7, 6, 5, 4, 3. And then if we look at the bottom line, 1, 2, 3, 4, 5, 6, 7, 8, 9 times 8 plus the 9, which is the last digit that I added to the previous ones, equals 987654321. Just kind of a cool pattern when you look at it. Well, here's another one. Here I'm taking 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 9. There's no 8 in there. And I'm multiplying it by 9, which is 9 times 1. And then I'm multiplying that same bunch of numbers by 18, which is 9 times 2. And then I'm multiplying it by 27, which is 9 times 3. And look at the interesting result. 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, etc. 3s, 4s, 5s, 6s, 7s, 8s. And then the bottom line, 1, 2, 3, 4, 5, 6, 7, 9 times 9 times 9, which is 81, equals 999999999. So you can play with things and kind of come up with your own patterns, or research some on the internet. You can find some really interesting patterns. I mean, there's a ton. I just recently took a graduate course with the Colorado State University, and one of the things is to inspire teachers and students with math. And part of the presentation that I'm sharing with you is from Math Wonders, a book, and there's a ton of different interesting patterns in there. Let's get exponents involved. We'll take the math level up just a little bit to include exponents. So again, carefully chosen numbers. 135 is 1 to the first power, 3 to the second power, 5 to the third power, right? 175, we take 1 to the first, 7 to the second, and 5 to the third power, and so on. 598, well, that's 5 to the first power plus 9 to the second power plus 8 to the third power. Kind of interesting. Well, if we go on, 1306, we're going to extend to now to the fourth power, and watch. 1 to the first, 3 to the second, 0 to the third, plus 6 to the fourth. If you figured all those out, right? And so exponents work like 3 to the second power means 3 times 3, okay? 6 to the fourth power means 6 times 6 times 6 times 6. And if you were to add those together, you would get 1,306. Then you look at, we'll just jump down to the last one here, 2,427. Well, that's 2 to the first power plus 4 to the second power plus 2 to the third power plus 7 to the fourth power. Figure all those four calculations out individually, add them together, and you get 2,427. That doesn't work for every number. These are, as I said, carefully chosen numbers, and maybe you can find some others, whether you want to look online, whether you want to just play around and see if you can discover other ones. So just, again, fun with patterns. And there's an unlimited number of different patterns. We could spend the whole hour just looking at numerical patterns like this. But that gives you an idea, I hope, of some things that are, oh, that's interesting. And that's kind of all the response I'd be looking for. Like if we were in an audience and you were here in person, you know, I'd just like to see some heads nodding and say, oh, you know, just kind of, oh, it's kind of interesting. It's not earth-shattering. It's not going to solve the world's problems, but it's kind of neat. So this is where you need your pen and pencil. Pen, pencil, paper. Now you need to follow the directions carefully. If you don't follow the directions carefully, it's not going to work. But I'm going to predict your answer, okay? So to start with, you need a 3-digit number where the first digit and the last digit are not the same. In other words, the hundredths place digit and the units place digit have to be different. So like 545, can't use it because 5 and 5, you can't. You know, the first and the last digit have to be different. So 647, 723, whatever you want. Write down a 3-digit number. So the first digit and the last digit are different. Okay, we're good. You have that written down. Now, on the paper, next row down, reverse the numbers. So if you wrote down 247, write if you wrote down 247, write 742. So you're reversing the 3 digits. Okay. Next step, subtract the smaller from the larger. So depending upon what number you started with and how you reversed it, you just want to subtract whichever is the smaller number, subtract it from the larger number so you don't end up with a negative number. Okay, so go ahead and do that subtraction. And then put a box around that result, okay? Just put a box. I don't have that direction written down, but put a box around that result you just got after the subtraction, okay? Now, the number that you have in the box, reverse those digits. So they're the other way around. If you ended up with 234, write down 432. So you're reversing the digits of the difference you have. Okay. Now put a circle or an oval around those digits of the difference. So you have an oval around the number you just wrote down. You have an oval around those numbers. Okay. Add those last two numbers. Add the number that you have in the oval with the number you have in the rectangle or the square. Add those two numbers together.
Dave,
Okay. Yeah.
So there's a question about step 3. So could you just start at the beginning and go through each step again, please?
Of course. Of course. So you're choosing a 3-digit number. The first digit and the last digit have to be different. Step 2, you're going to reverse them around. So if you wrote down 2, 3, 7, you're going to write down 7, 3, 2. Okay. So now you're going to subtract the smaller number, which would be the 2, 3, 7. You're going to subtract that away from the 7, 3, 2. So whichever the larger number of those two, you have your original number and you have the number with the reverse digits. Take the smaller number and subtract it from the larger number. Okay, did that help? That's pretty much the answer to step 3. Okay, and then I asked you to put a square or a rectangle around that subtraction. The answer to that subtraction problem, you have a rectangle around it, it's a positive number. Then you're going to take that number in the rectangle and reverse those digits. So if you got 9 to 7, you're going to write down 7 to 9. And you're going to put a circle or an oval around the number that is reversed. And then you're going to add them together. You're going to add the number that's in the rectangle plus the number in the oval. And you get an answer. Okay, is everybody good? I'm going to tell you what your answer was. This is your answer. Are you ready? You got 1,089. If you did it right. How many got 1,089? Hands are going up all over the place. Wow, look at that. Crazy. Okay. So plenty of people got the 1,089. So kind of cool. Again, we're doing something at the moment, just enjoying what we're doing. And you can study in a little more detail why that happens. There's actually an algebraic way that I could show you of why that happens that way, but that's a little beyond what we're doing right now. Is there a question?
I have a question because I got 198, so I clearly did it wrong.
Yep, you did it wrong.
My first and my third digits were different, but my first and my second digits, those were the same.
I think that's okay.
Okay.
I haven't tried every possible combination.
Okay.
But
so I'll see if I could do it again. But I clearly can't follow directions.
yeah, this is actually a good problem to use in like a math class, or really any class, but a math class, to see, can you follow directions? Okay. So the fabulous Fibonacci numbers, maybe you've heard of them. I just was actually at a meeting on Monday night, a few nights ago, and we were chatting, and I forget even how it came up. I think we were talking about rabbits. And I said, did you know that rabbits have to do with Fibonacci numbers? And they're like, what? Yes. So Leonardo of Pisa, I'm not sure how he got named Fibonacci, but Leonardo of Pisa was his name. And he wrote Liber Abaci, and that was in 1202. So obviously 800 plus years ago, he wrote this. And it started out with this problem. I'm just going to read what you see on your screen. How many pairs of rabbits will be produced in a year, beginning with a single pair of adult rabbits, if in every month each pair bear a new pair, which become productive from the second month on? So as you know, rabbits proliferate quite rapidly, rabbits rapidly. And then the last piece here is assume a pair of baby rabbits matures in 1 month. Now that's a little bit of a stretch, but again, the idea is this is just a math problem, a mind problem. What kind of numbers do you come up with? So you assume a baby pair of rabbits mature in 1 month to become offspring producing adults. And offspring producing adults are represented by capital A. Baby rabbits are represented by B, but they become producers after a month or in their 2nd month. Okay, so that's the problem. So Leonardo of Pisa, of which I believe the Leaning Tower of Pisa is the same one. So I'm not going to read every single line to you, but you see there's a pattern. We're starting with an adult pair. The adult pair have a baby or babies, reproductive babies, and the adult continues to be alive. The adult doesn't go away. So now in this year here, we have a pair of babies and a pair of the original adults. This adult has a pair of babies and continues to live. The baby, the babies become adult producers. So we have a pair of adults here. So here we have total of 3 pairs. How many pairs of babies? Well, there's 1 pair of babies here. So that's this one in the middle. Pairs of adults is here, it's 2. And so again, I'm not going to go through every line, but the important thing is you can see the pattern perhaps. So down to this line, this adult continues to live. The adult has a pair of baby rabbits. This pair of baby rabbits become producing adults. This adult pair continues to be an adult pair, but also has a pair of babies. This adult pair continues to live and be an adult pair, but also has a pair of babies. And this pair of babies from this row now become producing adults. And so if we were to add them up, you'd see we had 5 pairs of adults and 3 pairs of babies for a total of 8 pairs of rabbits. And so it continues. And so if you look at the numbers, you can see a pattern going on here. 1, 2, 3, 5, 8, 13, 21, 34, etc. And the same in this row, 1, 2, 3, 5, 8, 13, 21, 34, 55. And in the total pairs, the same sequence is there. 1, 2, 3, 5, 8, 13, 21, 34, 55, etc. And that is known as the Fibonacci sequence. And one way that you can figure it out is you start with the number 1 and you add 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. So you see the next number is the addition of the previous 2 numbers. 13 plus 21 is 34. 21 plus 34 is 55. And that same sequence happens in each of the rows, and they're offset by 1 because we're starting with adults that don't have babies yet, and then we have babies, but then we have the total of the adults and the babies. So you have the same sequence, but the rows are just off by 1, if you understand what I'm saying there. So who knew? This very famous sequence called the Fibonacci numbers all started with rabbits. Now, an interesting thing about these Fibonacci numbers is they're related to something else that's unrelated. The golden ratio. Just before I talk about that, the Fibonacci sequence is very well known in nature, and I would encourage you to Google. Like, there's a ton of pictures that you could get. There's pine cones, sunflowers, which are depicted here, but you kind of see the spiral effect here. And if you were to count as you move out, you're going to find these numbers. Look at here. Can you see there's a 1, a 3, a 5, an 8, and these are squares or rectangles, and the numbers represent the area. And see how we got 1, 3, 5, 8, 13, 21, 34, and it could continue around and around in a spiral fashion, and it creates the Fibonacci sequence. And it's seen in nature, in sunflowers, ferns, snails, other types of flowers. Daisies is also one. Galaxies that we see in the universe, even hurricanes, storms. We see that pattern, the Fibonacci pattern. It's amazing. Who knew? So you can Google that for yourself, Fibonacci numbers in nature, and you can see more specifics. So a little more mathy with the Fibonacci numbers. This is kind of interesting. If we take the Fibonacci numbers and we take the higher number and divide it by the adjacent lower number, so that's what this means, the function of n plus 1 divided by the function of n. So we have 2 divided by 1, we get a result. Then we get the next Fibonacci number, 3, and divide it by 2. And then we get the next Fibonacci number, which is 5. So you can see the numerators of the Fibonacci series, 2, 3, 5, 8, 13, 21, etc. And it continues in the second column. And we're dividing it by the denominator, which is 1 less on the Fibonacci series than the top number. So 2 over 1. So you can see the denominators follow the same pattern. 1, 2, 3, 5, 8, 13. Continue in the next column. But notice what the results are of the division. Notice what the quotient is when you divide the denominator into the numerator. We're starting 1, 2, 1.5, 1.6. Now, interestingly enough, once we get to 1.6, that 1.6 continues, and we get more results to the right of the decimal point, to the right of the 6. And as we continue over here, 144 divided by 89, 1.6179, 1.6180, 1.6180 again, 1.180 again with a 3. Then when we get to 987 divided by 610, we get 1.61803. Again, we got exactly the same thing with 5 places after the decimal point, and we could continue on. And the interesting thing where I was saying that these Fibonacci numbers are related to something that's unrelated, called the golden section, sometimes the golden ratio, the golden rectangle, and that's represented by the Greek letter phi, P-H-I, some pronounce it phi. The proper pronunciation in Greek is phi. And you get this ratio, 1 to 1.618, and that's all I would ask my math students to memorize, and they need to memorize what is the value of phi, what is the golden ratio, 1.618. Crazy, huh? Well, I talk about the golden section, the golden ratio. Well, here it is. Here's just one example of many. Again, I'm hopefully bringing you some topics that you might find interesting to encourage you to, go dig out more information on your own. Any one of these topics we could spend the whole hour on, but I'm trying to, broad brush stroke a lot of different things that I hope some of them you might find interesting. So Length to width. In the Parthenon, the length to width ratio is 1.6. The length to the width is that ratio that we got up to with the Fibonacci numbers. Remember, 1.618. And how do you, suppose I wanted to draw a golden ratio? Well, 1.618, that's, how do I measure that? Well, this is how you can construct a golden section. You start with a square, any square, but be sure it's a square. You find the midpoint, that's what the M stands for, the midpoint of one side of the square. Now you need to either use the old-fashioned string with a thumbtack, excuse me, string with a thumbtack and a pencil to make the arc, or hopefully you may have an actual mechanical compass or an architect's compass in your house, and you put the point of the needle on the M, and then you extend the pencil part to the corner of the square where point E is, and then you construct an arc. And when that arc comes down to meet the baseline here, now you can construct your rectangle, and that rectangle will have exactly the 1.618 ratio of length to width. And you have constructed a golden rectangle. Pretty cool. And who knew what you're looking at came from rabbits? So this is a fun little game that anybody in the family can play. Mirka, warning, warning, you have to follow directions.
Okay, I will do my best. And thank you very much to Melissa Quinn for explaining to me where I went wrong. I needed to add a 0 before and after the difference between those first two numbers so that I have 3 digits for the next part. So thank you. I appreciate that.
Good, and that's a good tip for me in case somebody else runs into that. Thank you. Okay, so I'm gonna guess where you're going. From Earth, are you going to Mercury, Venus, Saturn, Uranus, the asteroids, Pluto, Neptune, the moon, Jupiter, the sun, a comet, or Mars? Where are you going? Okay, so these are the instructions. We're starting on Earth, and we start on Earth, and I want you to choose a number from 5 to 15 and count your way around. So the first red arrow would be 1. The second red arrow would be 2. And then count your way around. Count to 5, anywhere from 5 to 15, okay? Starting on Earth, and then you're counting 5 to 15 places. The first red arrow right here, that's 1. Second red arrow is 2. Mercury is 3, etc. And you're going to go around. And where did you land? Okay, so everybody knows where you landed. Is everybody good? You know where you landed. From Earth, you counted so many spaces, and you're going around counterclockwise, and you landed somewhere. Now, from where you are, I want you to go backwards in the opposite direction, that same number of spaces. So if you went 6, I want you to go backwards 6. And pay attention to where you land. All right, so I trust that you have landed somewhere. And now, what I would like you to do is, from where you landed, I want you to count 4 spaces Hang on a second. So from where you landed, I want you to count four spaces. No, you know what? Don't count four spaces yet. Because, so where you landed, remember where you landed. You're not on Mars. I'm going to make the counting easier for you. You're not on Mars. You didn't land on Pluto. You didn't land on Uranus. And you didn't land on there. Okay, so pretty interesting. So now count four spaces, either clockwise or counterclockwise, it doesn't matter. From where you are, count four to the counterclockwise or four clockwise. And where do you land up? And I know where you landed. You landed on Saturn. True? How many landed on Saturn? The number keeps growing. Yes, you landed on Saturn. So the math piece to let me, explain, well, how do I know that you landed on Saturn? And if you do this twice, you probably can figure it out. And you might have figured it out the first time through, but just a little bit. How did he do that? Well, we started on Earth, and then I asked you to count 5 to 15 places using the first arrow as 1, the second arrow as 2, and then 3, 4, 5, etc. Okay. And so you went around counterclockwise somewhere between 5 and 15 spots. Then after you did that, I took away, oops, sorry about that. I took away, and I'm going to leave it up here for a second. I took away Earth and these two lines. Well, from Earth, if let's just say you went 6, and I don't know what number it was, but it really doesn't matter. But from Earth, let's say we went 6. 1, 2, 3, 4, 5, 6. So you ended up on Uranus. And then I took away Earth and the 2 arrows, which I'm not going to do right now because apparently I didn't have that program. So now I took away Earth and the 2 red arrows, and I asked you to go in the opposite direction, the same number of places. So from Uranus, where you are, going the other way, 1, 2, 3, 4, 5, 6, and you ended up on the sun. Everybody ends up on the sun. So if you can see it from here, from Mercury, right? We came from Earth, 1, 2, 3. And if we were going to go back to Earth, we would go back to Earth 1, 2, 3. But I got rid of Earth and the 2 arrows. So when you go back from Mercury, 1, 2, 3, you're always, everybody ends up on the sun. And so now that you're on the sun, I can say, well, you're not on Mars because I know you're not there. You're on the sun, and I know you're on the sun. You're not on Uranus, you're not on Pluto, you're not on the moon. So when I take those away, then I ask you to go 4 in either direction because Mars is no longer there. When you go 4 places, you go 1, 2, 3, 4, you end up on Saturn. And if you go the other direction, because remember, the moon and Pluto are no longer there. From the sun, you go 1, 2, 3, and Uranus isn't there. So moon, Pluto, and Uranus are gone. So from the sun going backwards, 1, 2, 3, 4, you're on Saturn. So whichever way you go, clockwise or counterclockwise, 4 spaces, you end up on Saturn. And so that's how I know you're on Saturn. And you can invent, a game like that yourself if you'd like to, something to play with. So some simple math, but it's kind of a fun game to play. Okay, I'll just pause there. Any questions so far? Any comments so far?
Well, I'm happy to report that I did it correctly. So I ended up on Saturn and I followed directions
Okay,
as
Mira,
requested.
thank you. Thank you for
Yes.
the report. That's encouraging.
And then I think this was, hitting on the previous example when we were choosing numbers and figuring out what our number was, and then you guessed all of ours. There was a question about the algebra behind this.
We don't have time for that. That's 10 minutes itself. It has to do with assigning the hundreds place 100 times h, which is the number that would represent times 100, then a t times the 10 representing the tens place, and then an o for the ones place with a number, maybe it's an o again, that represents the value of the ones place, and then doing some manipulation, which, as I said, would probably take about 10 minutes to go through. So it is pretty interesting. I will, again, mention that book, Math Wonders. It's in there, and I can share a little bit about that and the author at the end, because I definitely want to give him credit because I enjoyed the course that I took, and that's where most of these nuggets, not all of them, but most of these nuggets came from. So good question. We just don't have time.
Yeah. So something for someone who's really interested in this, a way for them to maybe follow up on their own and do a little exploration.
Yes. Okay. So here's a problem. You have a chessboard, and you're going to have 32 dominoes, because you probably know there's 64 squares. A chessboard, or a checkerboard, if you will, either way, is 8 by 8. So there's a total of 64 squares on a chessboard. And there are 32 black squares, and there's 32 white squares. So you're given a chessboard and you get 32 dominoes, each the exact size of 2 of the squares on the chessboard. So one domino will cover 2 adjacent squares on the chessboard. Can you show how 31 of these dominoes can cover the chessboard when you remove the opposite diagonal squares? Okay, so 32 dominoes would cover a chessboard that has 64 squares. Well, we're going to remove the two it doesn't matter whether I remove the 2 opposite blacks or the 2 opposite whites. It doesn't matter. But we're just going to go with removing the blacks, because that's what the illustration I have for you shows. And so the question is, how can you place, and I only need 31 dominoes now, right? Because now I only have 62 squares left on my chessboard. So how can you arrange 31 dominoes so they completely cover every square on the chessboard? I'm just giving you a little bit of time to think, maybe 30 more seconds. Okay, time's up. How do you do it? Well, sorry to be tricky. The answer is you cannot do it. It's impossible to do it, right? Adjacent squares on a chessboard are opposite colors. When you put a domino anywhere on a chessboard, it has to cover two colors. You put a domino on a chessboard, it has to cover a white and a black. Has to. So I've removed two black squares. So it's not possible for 31 dominoes to cover. If I removed a black square and a white square, now the black and white squares would be equal and I could do it. But if I remove either two black squares or I remove two white squares, can't be done. Sorry if I tricked you. Now, here's some math. Everybody likes fractions, right? Reduce these fractions. 16 over 64, 19 over 95, 26 over 65, 49 over 98. You have your paper and pen. How do you reduce these fractions? Well, let me show you an easy way to do it. Ready? The sixes cancel. You get 1/4, which is the correct answer. 19 over 95, cancel the nines, and you get 1/5, which is the correct answer. 26 over 65, the sixes cancel, giving you 2/5, which is the correct answer. 49 over 98, you can see the answer's a half. Cancel the nines, you get 4 over 8, which reduces to a half. That's an easy way to reduce fractions. We can do bigger fractions too. How about 484 divided by 84847? Or 3243 divided by 4324. How do we reduce those? Same technique. Cancel the 8s, cancel the 4s, and we end up with 4 over 7, which is the correct answer. The bottom one, 3243, 4324, the 3s cancel, the 2s cancel, the 4s cancel, leaving you with 3/4. I mean, that would have been a tough problem to reduce, but we cancel and we get 3/4. Done. The next slide is critical. No, don't do it. These were just carefully chosen coincidences. And the question is, can you make some more? That's not how you reduce fractions. And, you know, we could go into greatest common factors and prime factorization of the numerator and the denominator, so we could get every fraction reduced. But hopefully we know enough about the largest divisor that goes into both the numerator and the denominator, and we reduce fractions that way. Not this way, but pretty clever, huh? If you were trying to show somebody for the first time how to reduce fractions and you showed them this, they'd believe you, but their math lives would be forever ruined. One of the laws of education, the law of primacy. You know what the law of primacy is in education? The way you learn something the first time is the way it's going to stick, or it has a higher degree of likelihood that it's going to stick. So the law of primacy, don't teach people bad stuff, at least the first time. Okay, kind of cool. So this is one of my favorite problems. So I'm going to give you some time to think about it, not a whole lot of time, maybe another 30 seconds. I'll read the problem with you and then think about it. And this is going to be a little bit of circular geometry involved, but consider the globe of Earth with a rope, obviously a very long rope, like 24,900 miles of rope, is wrapped around the equator of Earth. Okay, and it's tight. It's right on the land, it's right on the water. Now we're going to splice into it 1 additional yard. So we're gonna like cut the rope, insert 1 yard extra, and wrap it up, tape it up. So now we have a complete circle of rope that's 1 extra yard long. And now it's not exactly touching the ocean or touching the land. It's a little bit loose. So the question is, will a mouse fit under the rope? Think about that for another 30 seconds. Do you think a mouse could now fit under the rope?
So Dave, just so that you know, in the chat box, we've got both a yes and a no answer so far.
Okay, one of them's right. All right, let's take a look. So with my, you see my little cursor here. So we have the small r is the radius of Earth, okay? The capital R is the radius of the rope that has the 1 extra yard inserted into it, okay? So small r is the radius of Earth when the rope was snug, and capital R is the radius out to the rope that is a little bit, we don't know how much yet, but a little bit higher than the surface of Earth. So, can a mouse fit under it is the question. So here's some math. Remember the circumference of a circle is 2 pi r. 2 times pi, which we can abbreviate to 3.1416. And if you solve this for small r, which again is the radius of Earth, r is equal to c, which is the circumference, over 2 pi. And the circumference can be any number of any circle. So we don't have to put in the number 24,900. C stands for the circumference of Earth. So the circumference of the rope, would you agree, is 1 more than that. So whatever this is in yards, the circumference in yards, we're going to add 1 yard to it. And so the circumference now, C plus 1, is 2 pi capital R, right? Because capital R over here to the bottom left, capital R is the radius out to the rope. And again, if we solve for capital R, if we solve for the radius of the rope out to the rope, that's C plus 1 divided by 2 pi. Okay, pretty simple algebra, geometry so far. So what we're interested in is, well, how big is this gap here? Okay, what's the difference between the radius of small r and the radius of capital R? How much room is there from the rope to the surface of Earth? Well, we're going to subtract them. Basically, we're going to take the radius here, the radius out to the rope, and we're going to subtract the radius out to the surface of Earth. We're going to subtract capital R minus small r. And what that is capital R is C plus 1 over 2 pi. And small r, we figured, is C over 2 pi. So subtracting them, you have C plus 1 over 2 pi. Subtract the small r, which is the radius of Earth, C over 2 pi. Notice we have common denominators. What a blessing. So the answer is going to be over 2 pi, our common denominator. And what's C plus 1 minus C? C plus 1 minus C is 1. So the difference of the radius out to the rope and the radius out to the surface of Earth, is 1 over 2 pi, measured in yards because we're using yards. And that's a number. Pi is equal to 3.1416. Multiply it by 2. Divide that into 1. You can do it with a calculator. 1 divided by 6.28. And 1 divided by 6.28 is 0.159 yards, or 5.7 inches. Plenty of room. A rat could get under there. Hard to believe, isn't it? You wouldn't think it. And obviously somebody didn't think it. Somebody did. But when you just add 1 yard to the equivalent of 24,900 miles, change that to yards, and it creates over a 5.5-inch gap. Crazy. And you can play with this and figure out, well, you know, how much rope do we need? And we're not going to do that right now, but how much rope would you need to maybe just have it be 1 inch off? Well, you could play with this simple, relatively simple algebra and geometry and figure that out.
So Dave, I have to also share the comment that was made by the dailies. For people who have tried to figure out how mice are getting into their house, the answer is, if you had a coffee filter, a mouse would go through it and reconstruct himself on the other side. So there we go.
There you go.
Even with less than 5.7 inches, that mouse would definitely get through.
Absolutely true. It's amazing, isn't it? It really is. Okay, next on our show, I'm going to prove to you that 0 equals 1. I think possibly in the description of the Superstellar Friday, I might have said, I'm showing you that. No, I think that's what I said. No, I think I said, oh, this is wrong. The description was right. This should be 1 equals 2. I'm going to show you that 1 equals 2. Anyway, I'm not going to change my slide right now. You'll get the point. So we're going to start, and I'm going to show to you that 1 equals 2. And that should be, I'm sorry, the title of my slide here. 1 equals 2. Let's prove that 1 equals 2. So we're going to start with the premise A equals B. Easy enough. A equals B. You know what? No, that's fine. So now what I'm going to do is I kind of have what I'm doing off to the right side. I'm going to multiply both sides by A. And you know, one of the most important things when you're dealing with the equation, see these equal signs? To keep things equal, you have to do the same thing to the left side as you do to the right side. You have to do the same thing to both sides to keep them equal. So that's going to be what we're going to do throughout here, is to keep the left side and the right side the same operations happening. So I got A equals B. I'm saying that. It's true. A equals B. Well, then I'm going to multiply both sides by A. And if I multiply both sides by A times A is A squared. A times B is AB. So I have successfully multiplied both sides by A. Right? And everything's good. Now, what I'm going to do is I'm going to subtract B squared from both sides. So I've got A squared, and I'm going to subtract B squared. Well, if I do that to one side, I have to do it to the other. So I've got AB, and I'm going to subtract B squared, doing the same thing to both sides. So everything's legit. Okay, now factor. We all love, I'm just, as a matter of fact, in my algebra class, I'm just started today teaching factoring remotely. Well, we haven't got to this first one in our class yet, but this is a difference of 2 squares. A squared minus B squared, there's a rule. A squared minus B squared equals A plus B, in parentheses, times, in parentheses, A minus B. It's a rule. And then on the right side, AB minus B squared, I can factor a B out of that because a B is common. So when I factor, I get this. A squared minus B squared is, in fact, A minus B times A plus B. And when I factor out the B from the right side, that's B times A minus B. So that's true. I factored both sides. Now, as I look at these, I notice there's an A minus B on the left, and there's an A minus B on the right. So to make my life easier, I'm going to divide both sides by A minus B. So let me divide both sides by A minus B, and I get A plus B equals B, right? Because I divided by A minus B over here, so they cancel. I divided by A minus B over here, so they cancel. So I get A plus B equals B. Okay? So now remember, A and B are equal to each other, right? This is important. A equals B. So A equals B. So B plus B is 2B, or not 2B, right? I always say that. My students are sick of hearing that. But anyway, so A is the same as B. B plus B is 2B, and then I just have a B over here. Divide both sides by B. 2B divided by B is 2. B divided by B is 1. Cogito ergo sum. 2 equals 1. Ta-da! I proved it. 2 equals 1.
So Dave, there was a question about this, or a comment. If A equals B, A minus B would be 0. So wouldn't you be dividing both sides by 0?
Who said that?
It looks like Ovi or Avi said this.
Give them a free pass to something. You're right. That's it, dude. You can't divide by 0. Good job. So down the bottom, I have ta-da. No, not ta-da. If A equals B as we stated, then A minus B equals 0, and division by 0 is not allowed. And that was the peculiarity. I do this in my algebra class every year. And I would say not never, but rarely does somebody get it. And this is like one of the most important things that I'm teaching in my algebra class now. Whenever you come up with a fraction with a variable in the denominator, you have to stipulate whatever the variable or the term is in the denominator cannot be equal to 0. Okay, good job, Ovi. But that's kind of a fun thing. So if you know a little bit of algebra to be dangerous, you can convince people that 2 equals 1. Okay, good job. All right. Finally, let's make a deal with Monty Hall. I remember watching this years ago. You know, as time goes by, people pass away. I feel really badly. Alex Trebek, Jeopardy was one of my favorite shows, still is one of my favorite shows. And I hope that you can watch a recording of it, because his last show that he recorded was aired tonight, and we missed it because we're all here. But I know I recorded it on our DVR, so we'll be watching it later or tomorrow. And Monty Hall is with Alex Trebek now. So let's make a deal with Monty Hall. Well, this is usually how the show ends, right? You have what's behind door number 1, what's behind door number 2, what's behind door number 3, because behind one of those doors is the car. And behind the other 2 doors are the goats. Now, I went shopping. I spent a ton of money to do this presentation, I want you to know. I couldn't find any goats. I got sheep, though. I got, I don't know, kind of a gray sheep and a white sheep, and it doesn't matter, but the show seemed to use goats, but anyway, we'll just pretend the sheep are goats. So we've got two, I'm going to call them goats, okay? I know they're sheep, and any little kids watching would know that's not a goat, that's a sheep. It is. I'm going to call them goats. And a car. So behind one of these doors is the car. And so the contestants that won the most money, whoever, you know, gets to come down and choose, well, what door is the car behind? Well, behind one of the doors, and this is just a sample, right? There's the car, and behind the other two doors is the goat. So it doesn't matter, you know, where the car is or where the goat is. The point right now is to help you improve your odds by twice if you were to play this game, okay? So let's see. I think you would agree with me that each door has the same probability, 1/3. There's a 1/3 chance the car is behind door A. There's a 1/3 chance the car is behind door B. And there's a 1/3 chance the car is behind door C. That's true. Well, we know there's two goats and there is one car. So let's just play for a minute. This is just going to take I think a quick moment, because me and my wife, we spent all day trying to work this out. So I got to move my computer around, so there'll be a little motion. If I touch the wrong thing on my computer, I may lose you and I may have to come back. I don't know. I hate moving my computer around because you never know where your fingers may accidentally land or what cord might come unplugged. So anyway, just give me a moment. It'll be, I think, a quick moment. I've just got to move my computer. Okay, so computer moved. We have a car. I'm going to carefully tilt my camera down so you can see the car. And I've got my two goats, okay? And I have doors. I'm going to move these around, so don't think they're going to stay there for a minute, right? So I have door number 1. Hopefully that'll stay. I have door number 2. And I have door number 3. Okay, now, I don't know if you can kind of see what I'm doing behind the scenes here. I don't know if you can or not. So I'm trying to be sneaky. And if you can see, well, that's cheating. Put your blindfold on. Okay. So I have positioned the goats and the car. And I know I'm kind of behind here, but I'm not the important thing. So what I'm going to do, like, real quick then is, hang on a moment, is stop sharing. So this gets a little bigger. And so you can see door number 1 and door number 2 and door number 3. So who wants to play? So Merker, tell me, who puts their hand up first?
Well, we've already actually got a vote by.
No, I don't want any votes. I want somebody
votes.
who wants to play. Who wants to raise their hands to play?
Okay, first hand up was Amy Malahi.
Okay, Amy, behind what door do you think the car is?
So Amy, I have unmuted you if you want to then unmute yourself and talk.
I think I did. Can you hear us?
Yep.
Yep.
Okay. So this is my son Hazen. He's gonna play for me.
Okay,
Or the pick.
Pick which? Pick.
3.
okay. So what's his name? Hayden?
He's in.
Hazen. Okay, so Hazen says it's behind door number 3. Okay, so what I'm going to do is, as Monty Hall would do, right? But this is, let's make a deal with Dave McDonald. I'm going to reveal one of the doors. And obviously, I'm not going to reveal the door that you chose. And I'm not going to reveal the door that has the car, which may or may not be the same as the door that you chose. So I'm going to show you a goat, right? Definitely, I'm showing you a goat. Okay. So now, Hazen, my question is, and this is for the car. Do you want to keep door number 3, or would you like to change to door number 1?
Keep 3.
You're going to keep 3. Okay.
I think this is a trick question.
Ready? So this is what you got. You kept door number 3. And you get goat.
Goat. It's a sheep, not a goat.
I know, but we're calling them goats tonight. The car was behind door number 1. And good job, Hazen, because you illustrated my point. And I'm going to explain it to you a little bit mathematically with probability, but you double your chance of getting the car if you switch. A lot of people think, well, at this point, it's 50-50. It doesn't matter, right? It's 50% number 3 or 50% number 1. And that's not true. That is absolutely not true. You have twice the chance of being right and getting the car if you switch doors. If you keep the same door, you have a 1/3 chance of being right. If you switch doors, you have a 2/3 chance of being right. It's not guaranteed that you're going to be right, but your chances are double if you switch doors. So I'm going to explain to you why that is. Okay, so hopefully you had fun. We played it, and Hazen, that was a perfect example. It would have been so sad if you won.
Thank you.
You're welcome. So I hope that you can stay and maybe understand. The math is really, I think, fairly simple. But a lot of people, even some mathematicians, don't believe it. Even some mathematicians think it's 50-50 at that point. It's not true. It's not true. So I'm going to move my computer back closer to me without hopefully disturbing any keys or any wires. And I'm going to go back to sharing my screen to explain it. And you may not understand it the first time through, because it takes a while sometimes to process. I think some people will get, oh yeah, I understand. And some people are like, what? I still think it's 50-50. It's not 50-50. All right, so let me share my screen again. So before we start, we agree that it's a 1/3 chance the car is behind any of the 3 doors. It's an equal chance, 1/3. Now, if I have the right slide here, let's just say I reveal, now this is important, and okay, so this is actually like what you did, Hazen, right? You said door number 3 was your choice, and I revealed the goat behind door number 2. Now, when we started, each door had a 1/3 chance. So would you agree with me or not that when we start, one has the car, which is a 1/3 chance, and the other 2 doors have a 2/3 chance of being the car, right? So if I go back, can I go back? Yeah. So one door, whichever it is, has a 1/3 chance of being the car, and the other 2 doors together have a 2/3 chance that it's behind one of the other, right? It's a 2/3 chance it's behind B or C. 1/3 chance it's behind A, 2/3 chance it's behind B or C. Okay, so remember that. So 1/3 chance it's behind 1, 2/3 chance it's behind 2 or 3. I show you 2. So now that 2/3 chance goes all to door number 3. Okay, does that make sense? There's a 2/3 chance the car is behind 2 or 3. This, I know this is not exactly the choices you made, but you understand? I'm explaining it again. It takes a few times and maybe more times than we have time for tonight. But there's a 1/3 chance it's behind any one of the doors. There's a 2/3 chance it's behind either 2 or 3, or 1 or 3, or 2 or 1, right? So since there's a 2/3 chance it's behind 2 or 3, if I show you 2, because I'm not going to show you the door with the car, and I'm not going to show you the door that you chose, and they might be the same, but I'm not going to show you those doors. I'm showing you for sure a door with a goat. So the 1/3 chance of that being the goat shifts to the door that you did not choose. So you are in a better position to change your vote always. Not say it's not a guarantee that you're going to win. So it's not like, well, I lost, so he's wrong. If we played the game, which I just played with you, if we were able to, if we had the time to, and it would be fun, for everybody, and I don't know, other 24 people, however many people are out in the audience, if we were able to play the game so all 24 people could play it, I think we would see that somewhere around 8 people would lose and 16 people would win by changing the door. And 24 is a small sample, but approximately. The more people you have play, the closer it gets to be the mathematical average or the predicted average. Okay, so that's it. Let's make a deal. Keep your door. You have a 1/3 chance to win, because when you started, it's a 1/3 chance. You keep your door, you still have a 1/3 chance you're going to win. With the goat displayed, change your door and your chances improve to 2 out of 3, which is like 67% chance instead of 33% chance. So there you have it. I hope you had a fun time. Thank you.
Thank you very much, Dave. I learned, first of all, that I need to do a better job of following directions, but I also definitely enjoyed seeing all of the ways that you can have fun with math, even on a Friday night.
Absolutely, on a Friday night. So thanks everybody for coming. Hope you did have a good time. And
you wanted to mention that book again.
I did. So hang on just
Yep.
a second, if you can bear with me a moment. Don't go away. I know you're not seeing my screen, and that's fine. I will, oops. Hang on. There we go. Oh, I see. Hang on. Don't go away. Don't go away. It's going to take another second.
Okay.
It's going to just take a quick second here. A quick second. That's like whatever, that's
So
almost like
someone has asked the question while we're waiting, why do you say fun spelled with PHUN?
because it's fun. It's different. That's all. It's just different. It's just it's just fun, right? Isn't it? Didn't it get your attention? It must have,
Exactly.
because
You wonder, spent the whole
because
time
you
wondering.
wonder, and
about
so
it.
you know, I had you on my hook. That was my hook for the whole thing. Is he going to explain it? Well, I didn't, but you asked, and so now I
I had
explained
to
it.
ask the question.
Yeah.
Great.
So
So I
don't.
want to thank everyone again while Dave's finding the book information. Thank you for
Yeah.
joining us. You will be getting an email tomorrow, 24 hours later, that once again thanks you, but also asks for any comments, questions, suggestions that you might have. And all of that will go to me. So I'm happy to, you know, take in any suggestions that you might have for future topics. If you have questions for Dave, after this, you can send them to me and I will certainly send them on to him, or you can go to starhop.com and you'll find his contact information there as well. And you can send him questions. We have been doing Superstellar Friday as a virtual event since the summer, and we're going to keep going forward. So we do have one planned for February as well. It'll be the first Friday of the month. And we've got a guest speaker coming from, or Zooming from, the Harris Center in Hancock, New Hampshire, and she's going to be talking about an earlier time period in New Hampshire's geologic history. So you can find that information. We'll put that up on the website probably next week, and you can get all of that there and register for that if that's interesting to you. But Dave, you found the book?
I did, but then now my hang on, I gotta get to the correct slide, which I made the first slide like so. So maybe you can see that.
Yep, I see. Math Wonders to Inspire Teachers and Students.
By Alfred
Awesome.
S. Poser Mentier.
Awesome. Thank. Wonderful. So for those of you who were wondering why some of these things worked, or wondered what other possible problems could you approach through the lens of math, here's something to do maybe on a really snowy winter's day or something like that. When you're stuck inside, you can start exploring the world of math even more.
Yeah, it's a great book. There's so much in it, and I really had, you know, one of the tough times I had in preparing the presentation was, you know, what do I talk about? What do I not talk about? There's just so much stuff. So hopefully that was you know, and I again appreciate your comments, your feedback. Hopefully that was you know, kind of a broad spectrum of different kinds of things you can do with math and have some fun with it.
Yeah, it was great. I enjoyed it. I believe that everyone else did too. So thank you very much. And thank you everyone as well. I hope you have a great rest of your evening, great weekend. Hope 2021 is off to a good start as well. And we hope to see you back again sometime. So thank you all. Have a good night.
Bye-bye. Good night. Keep having fun with math. PHUN.